Right now, somewhere in a massive, hyper-cooled server farm, thousands of state-of-the-art graphics processing units are screaming at their absolute thermal limits. Fans are spinning at tens of thousands of revolutions per minute. Industrial water chillers are pumping millions of gallons of sub-zero liquid through labyrinthine pipes, and the local power grid is straining to deliver the equivalent electrical load of a medium-sized city just to keep those tiny squares of silicon from literally melting themselves into useless slag. The heat is overwhelming. The energy consumption is astronomical. And this is just to train the current generation of artificial intelligence models. As we sit here looking at the physical infrastructure of the modern digital economy, we are hitting a terrifying thermodynamic wall. The entire global artificial intelligence chip industry, combining the output of every major manufacturer on the planet, currently produces roughly 20 gigawatts of computing power. That is the ceiling. That is what the collective engineering might of humanity has managed to piece together through decades of optimized, globalized supply chains. But then, a man walked onto a stage at the Seahome Power Plant in Austin, Texas, and fundamentally declared that the entire global architecture of silicon manufacturing is obsolete. Elon Musk stood there and unveiled a $25 billion joint venture between Tesla, Space Exploration Technologies, and Zappi. He called it the Terafab, and his stated goal was not to incrementally improve the current system by 10 or 20%. His goal was to achieve an annual computing power output of 1 terawatt. Let those numbers settle in your mind for a moment. He is proposing to outpace the collective compute output of the entire planet Earth by a factor of 50, and he plans to do it all inside a single vertically integrated ecosystem. Speaking as a serial founder, when I look at a business plan that proposes expanding a market output by 50 times, while simultaneously tearing down and rebuilding the entire established supply chain, my immediate instinct is to look for the single point of failure. Usually, an ambitious founder pitches a software scale-up where marginal costs drop to zero. But this is hardware. This is atoms, not bits. This is the hardest, most unforgiving physics imaginable. And Musk is betting $25 billion that he can vertically integrate the most complex manufacturing process ever devised by human beings. It is a proposition that borders on madness. To understand why this is either the greatest engineering pivot of the 21st century or a massive capital incinerating suicide mission, we have to deconstruct the fundamental problem with how the world currently manufactures silicon. We have to look at the invisible relay race that dictates the speed of global innovation. If you want to build a cutting-edge chip today, you are essentially orchestrating a multi-year, multi-continent logistical nightmare. It starts in California, where brilliant electrical engineers and systems architects spend years designing the logical pathways of the processor. They write millions of lines of hardware description language, simulating how billions of microscopic transistors will route electrical signals to perform complex mathematical operations. Once that digital blueprint is finalized, it is packaged up and sent across the Pacific Ocean to Taiwan. There, inside the multi-billion-dollar fabrication plants of companies like Taiwan Semiconductor Manufacturing Company, the design meets the physical world. The silicon wafers begin a months-long journey through hundreds of individual chemical and optical processes, extreme ultraviolet lithography machines, each costing hundreds of millions of dollars and containing mirrors polished to such an extreme tolerance that if they were the size of the Earth, the highest mountain would be a few millimeters tall. Blast patterns onto the wafers. They use lasers to vaporize microscopic droplets of molten tin, creating a wavelength of light that carves features smaller than a biological virus into the silicon. It is a miracle of modern physics. But it is painfully slow. Once the wafer is finally patterned, etched, doped, and cleaned, the relay race is still not over. The fabricated wafers, fragile and incredibly valuable, are carefully boxed up and shipped again, often to facilities in Malaysia or other parts of Southeast Asia. There, they undergo packaging and testing. The delicate silicon dies are cut from the wafer, mounted onto substrates, wired up to microscopic pins, encased in protective thermal spreaders, and rigorously tested for defects. Only after all of this, months after the initial design was sent out, does the final chip get shipped back to the United States, or wherever the end consumer is waiting to integrate it into a server, motherboard, or a vehicle chassis. In engineering terms, this entire global supply chain is a system plagued by massive latency bottlenecks. Every single border crossing introduces weeks of delay. Every handoff between different corporate entities introduces a potential quality assurance failure point. If you are an engineer working on the bleeding edge of artificial general intelligence, you realize very quickly that your iteration speed is not limited by how fast you can write software, but by how fast you can get new hardware to test that software. If you realize you need to tweak the architecture of your neural network accelerator to handle a new type of floating point calculation, you cannot just compile a new chip in an afternoon. You have to update the design, negotiate a new production slot with the fabrication plant, and wait half a year for the physical silicon to arrive back on your desk. This latency is fatal when the technology landscape is shifting on a weekly basis. Elon addressed this architectural flaw directly during the launch event in Austin. He pointed out the absolute necessity of being able to make a chip, test it on the spot, identify the physical or logical bottlenecks, change the design, immediately push that new design to the lithography machine. By bringing design, lithography, fabrication, and advanced packaging all under one massive roof, Tesla is attempting to treat hardware development with the exact same agile, iterative methodology that software developers have used for decades. They want to compile silicon the way a programmer compiles code. But there is a secondary, much more brutal reality driving this $25 billion gamble. Even if Tesla, SpaceX, and Xi wanted to continue using the traditional global supply chain, they simply cannot. They have hit the maximum structural bandwidth of the world economy. Tesla is already one of the largest consumers of high-performance compute silicon on the planet. But as Musk noted, even titans like Taiwan Semiconductor and Samsung have a maximum rate at which they are comfortable expanding their capital expenditures. Building a new fabrication plant costs upward of $20 billion and takes years. These legacy manufacturers are inherently risk-averse. They want guaranteed, long-term contracts from multiple diversified clients before they pour concrete. They are not willing to bet their entire corporate balance sheet on the explosive, exponential growth curves that Musk is projecting for millions of robotaxis and billions of humanoid robots. Elon put it with characteristic bluntness. He said they either build the terafab or they simply do not have enough chips to execute their master plan. The existing world cannot supply them, so they must build a new world. Looking at their business model canvas, however, they are introducing a level of systemic risk that would make any traditional board of directors sweat bullets. When you vertically integrate to this extreme degree, you achieve unprecedented speed and cost efficiency. But you also create a massive monolithic single point of failure. The traditional tech giants companies like Apple, Google, and Amazon specifically design their supply chains to be distributed. They split their orders across multiple fabrication plants in different geographic regions precisely to avoid catastrophic disruptions. If an earthquake hits Taiwan, or a localized power grid fails, or a critical chemical supplier experiences a shortage, a distributed system routes around the damage. By consolidating everything into the terafab, Musk is putting all of his chips on exactly one square on the roulette wheel. And the scale of that single square is almost impossible to comprehend. When drone footage first started circulating of the massive new plot of land being cleared and prepared near the existing Texas Gigafactory complex, industry analysts assumed it was just another expansion wing for vehicle production, or perhaps a battery cell manufacturing line. The render shown during the presentation looked enormous, roughly the size of the current Texas facility. But then Musk completely reframed the scale of the project on social media. He clarified that the massive building shown in the initial presentation was nothing more than an advanced technology fabrication lab strictly dedicated to rapid prototyping. It was just the laboratory. The actual full-scale terafab is something else entirely. He confirmed that the production facility will span approximately 100 million square feet. Let me try to contextualize 100 million square feet of ultra-clean vibration, isolated, high-tech manufacturing space. This is not a warehouse. This is not a standard assembly line where you can just pour a concrete slab and bolt down some robotic arms. Semiconductor fabrication requires environmental control that defies belief. The air inside the lithography cleanrooms must be thousands of times cleaner than a hospital surgical theatre. A single speck of dust landing on a wafer during the exposure process will destroy billions of microscopic transistors and render the entire chip useless. The floors must be decoupled from the surrounding earth, built on massive shock absorbers, so that the microscopic vibrations from a truck driving on a highway miles away do not blur the nanometer-scale lasers actively carving the silicon. Building 100 million square feet of this specific type of infrastructure means constructing an environment 10 times larger than the current massive Texas gigafactory, and over 30 times larger than the sprawling circular spaceship headquarters that Apple built in Cupertino. In pure square footage, it is comparable to taking the entire sovereign territories of Vatican City, Monaco, and Gibraltar and putting a single continuous roof over all of them. This facility is being engineered to handle an astonishing 1 million wafer starts per month. To understand the sheer arrogance and ambition of that number, you have to look at the current undisputed king of the industry. Taiwan Semiconductor Manufacturing Company, after decades of relentless optimization and hundreds of billions of dollars of investment across multiple massive facilities, produces a specific global output. This single terafab campus in Texas is designed to produce roughly 70% of Taiwan Semiconductor's entire worldwide output all by itself. It is a centralization of manufacturing power that has no historical precedent. But if you think the physical scale of the building is the wildest part of this business plan, we need to dive into the product mix, because this is where the engineering logic transitions from terrestrial manufacturing into orbital mechanics. Unlike conventional chip factories that operate as foundries, trying to build a wide variety of chips for a wide variety of customers, the terafab is ruthlessly specialized. It is split into two dedicated fabrication lines, each hyper-optimized for a specific proprietary architecture. The first line is dedicated to Tesla's inference chips, the hardware that actually runs the trained neural networks in the real world. This includes the AI and AI-Lu architectures, which will serve as the localized brains inside the upcoming Cybercab robotaxi fleet and the Optimus humanoid robots. Given that Musk estimates the Cybercab will outnumber all existing Tesla vehicles on the road today, and that the Optimus robots are intended to be manufactured in the billions, the volume requirements for this single terrestrial chip line are staggering. However, it is the second fabrication line that reveals the true terrifying scope of the master plan. The second chip architecture is designated the D3. This is not a standard processor designed to sit in a server rack in a data center in Virginia. The D3 is a highly specialized, massively powerful radiation-hardened processor engineered specifically to survive and operate in the harsh vacuum of low Earth orbit. And here is the data point that is currently sending absolute shockwaves through the semiconductor and data center industries. According to the stated production goals, fully 80% of the terafab's total, unprecedented compute output is destined for space. Only 20% of this massive 100 million square foot facility's capacity is staying on the ground to run the cars and the robots. Speaking as an engineer who has analyzed data center unit economics, this 80-20th split initially sounds completely backwards. Why would you incur the astronomical cost of launching millions of pounds of dense silicon hardware into orbit when you could just plug it into the terrestrial power grid? The answer comes back to the fundamental bottleneck I mentioned at the very beginning, thermodynamics. On Earth, cooling is the ultimate constraint. It is the ultimate customer acquisition cost of artificial intelligence. When you run a massive cluster of processors to train an advanced neural network, the electrical resistance within the silicon generates immense localized heat. If you cannot remove that heat fast enough, the silicon degrades and the system crashes. Terrestrial data centers spend an enormous percentage of their total operating budget not on running the computers, but on running the massive refrigeration systems required to keep the computers from catching fire. You are fighting the ambient temperature of the Earth, and you are fighting the limitations of thermal conductivity in the atmosphere. But low Earth orbit offers a thermodynamic arbitrage opportunity that fundamentally changes the mathematical equation of large-scale computing. Space is effectively a near-infinite heat sink. Now, it is important to clarify the physics here, because a vacuum does not actually conduct heat. You cannot blow a fan in space. Instead, you have to rely entirely on blackbody radiation to shed thermal energy. By designing massive, highly efficient radiator panels that point away from the sun and toward the absolute zero background temperature of deep space, an orbital data center can reject heat far more efficiently than a terrestrial facility relying on chilled water and ambient air. Furthermore, you have the energy input side of the equation. Down here on the surface of the planet, solar energy is filtered, scattered, and absorbed by miles of atmospheric gases and weather systems. A solar panel on Earth is subject to the day and night cycle, the seasons, and cloud cover. But in specific orbital trajectories, a solar array can receive completely unfiltered, unattenuated solar radiation 24 hours a day, 7 days a week. The energy density is roughly 5 times stronger in orbit than it is on the ground. When you combine 5 times the available continuous energy with an infinite naturally occurring heat sink, the unit economics of operating a massive artificial intelligence cluster completely flip. Elon is essentially proposing to physically move the central nervous system of the global economy off the surface of the planet. The terafab is just the terrestrial engine designed to manufacture the hardware for space exploration technologies' orbital data center constellation. They are planning to deploy a network of 1 million interconnected artificial intelligence satellites. This is why the integration with space exploration technologies is not just a corporate synergy buzzword. It is a strictly necessary component of the architecture. You cannot build a 1 million satellite data center constellation if you are waiting on the manifest of traditional launch providers. When you sit down and look at the raw, underlying numbers for Musk's various aspirational projects across his different companies, the terafab suddenly shifts from looking like a reckless gamble to looking like a mathematical inevitability. During the presentation, it was stated that the Starship launch platform, once fully operational and rapidly reusable, has the potential to deliver 10 million tons of payload mass to low Earth orbit every single year. Simultaneously, Tesla's energy division has been quietly but aggressively building up its internal capacity to manufacture a terawatt of solar power generation equipment annually. So, if you look at the system architecture from a top-down perspective, Space Exploration Technologies has built the heavy lift capacity to move the physical mass off the planet. Tesla Energy has built the capacity to generate the massive electrical power required to run the systems. But if you have the transport logistics and the power generation solved, you are still missing the actual payload. You need the silicon compute to actually run the intelligence at that exact same phenomenal scale. The terafab is the missing piece of the puzzle. It is the factory that prints the brains that Starship will carry, and that Tesla solar panels will power. We have seen this exact pattern of aggressive, preemptive infrastructure building from Musk before, and it is worth analyzing it to understand the current strategy. Back in February of 2014, the technology press and the legacy automotive industry collectively scoffed when Musk announced that Tesla was going to build the world's first gigafactory in the remote desert of Nevada. The skepticism was entirely logical at the time, based on linear thinking. In 2014, Tesla was barely surviving as a niche boutique car manufacturer. They were hand-assembling roughly 30,000 Model S luxury sedans a year. That was their entire operational footprint. Yet, they boldly announced a multi-billion-dollar facility designed to produce 35 gigawatt-hours of lithium-ion battery cells annually. To put that completely out of proportion scale into perspective, 35 gigawatt-hours was more than the entire global production of lithium-ion batteries for every single laptop, mobile phone, and digital camera on Earth combined. The critics laughed and called the Nevada Gigafactory a bridge to nowhere. They looked at the current demand for the Model S and correctly calculated that the factory was absurdly oversized. But they failed to understand the underlying engineering roadmap. They were building the foundational infrastructure for a mass-market vehicle that did not even exist as a physical prototype yet. They were building it for the Model 3. They understood a fundamental truth of manufacturing physics. The battery factory had to exist fully scaled and operational long before the mass-market car was even mathematically possible to produce at an affordable price point. If they had waited for the demand to materialize before building the supply, the entire product line would have collapsed. We all know how that specific gamble played out. Once the Gigafactory achieved economies of scale, the cost per kilowatt-hour of battery storage plummeted, enabling the Model 3 to eventually become the best-selling vehicle on the planet, ultimately paving the way for the even more dominant Model Y. Fast forward to today, and we are witnessing the exact same strategic playbook being executed, but scaled up by multiple orders of magnitude. Tesla and space exploration technologies are not building the Terafab just to run the current fleet of vehicles operating on the existing full self-driving software architecture. They are building it because you fundamentally cannot have a future world populated by billions of autonomous Optimus humanoid robots, millions of roaming robotaxis, and a million interconnected artificial intelligence satellites if you are standing in a queue waiting for microscopic chip allocations from an external supplier in Taiwan. In 2014, the critical existential bottleneck to the future was chemical battery storage. In 2026, the critical existential bottleneck is the physical processing of intelligence. The Terafab is the brute force solution to that bottleneck. But in true, relentless entrepreneurial fashion, even this massive earth-shattering facility is framed as merely a stepping stone. During the closing moments of the presentation, the narrative zoomed out even further, revealing the long-term architectural vision. Musk calmly clarified that achieving 1 terawatt of computing power through the Texas Terafab is only phase 1. To push the boundaries of artificial general intelligence into the realm of a petawatt of compute, which is the equivalent of 1,000 terawatts. The terrestrial logistics model completely breaks down. You cannot practically launch that much physical mass from the deep gravity well of Earth, even with a fleet of fully reusable starships. The fuel costs and atmospheric limitations become insurmountable. The proposed solution for the petawatt era involves utilizing the moon. The concept requires constructing a massive electromagnetic mass driver on the lunar surface. From an engineering perspective, this is actually incredibly sound logic. The moon possesses only a fraction of Earth's gravity and has absolutely no atmosphere to create aerodynamic drag or generate friction heat during a launch sequence. You could use vast arrays of solar panels on the lunar surface to charge massive capacitor banks, and then use that stored electromagnetic energy to physically accelerate payloads of silicon and structural components along a magnetic rail, launching them directly into lunar orbit or towards Earth orbit without using a single drop of chemical rocket propellant. This infrastructure would effectively drop the cost of launching massive space-based infrastructure to nothing more than the amortized cost of the solar electricity required to charge the magnetic rails. It is the ultimate circumvention of the rocket equation. When you synthesize all of these data points from the 100 million square foot fabrication floor in Texas to the orbital data centers to the lunar mass drivers, you begin to see the outline of a monopoly that makes the Standard Oil Trust of the 19th century look like a small regional business. If this $25 billion joint venture succeeds, Musk will have vertically integrated the fundamental resource of the modern era. In the industrial age, power belonged to those who extracted, refined, and distributed physical fossil fuels. In the artificial intelligence age, power will belong to whoever can design, manufacture, launch, and power the physical architecture of synthetic thought. By eliminating the global supply chain, by removing the reliance on legacy fabrication foundries, and by moving the most energy-intensive processes off the surface of the planet entirely. This architecture creates an economic moat that is virtually uncrossable by any competitor operating within the constraints of traditional terrestrial business models. If the Terafab reaches its 1 million wafer per month target, the cost per floating point operation will crash so hard and so fast that any company still buying chips from a third-party foundry and plugging them into a grid-tied data center in Nevada will be economically obsolete overnight. They will be trying to compete with a horse and buggy against a localized electric ecosystem. However, the teardown of this grand vision always comes back to the massive, undeniable risks of executing at this scale. The Terafab is a monument to vertical integration, but it is also a monument to hubris. If there is a fundamental flaw in the extreme ultraviolet lithography process they are attempting to internalize, if they cannot achieve the microscopic yield rates required to make the silicon economical, or if the intricate dance of robotic material handling across 100 million square feet of clean room floor falls out of synchronization, the entire $25 billion investment becomes the most expensive empty warehouse in human history. There is no backup plan. There is no secondary supplier to call. If the terafab stumbles, the robots stop walking, the cars stop driving, and the orbital satellites remain grounded. As an engineer, I look at the physical blueprints and the thermodynamics of the orbital computing plan, and I see a beautifully elegant solution to a terrifyingly complex problem. As a serial entrepreneur, I look at the capital expenditure and the concentration of risk, and my blood runs cold. The sheer audacity to look at the most complex, highly optimized, intricately balanced global supply chain ever created by human civilization, and decide that you can do it better, faster, and cheaper all by yourself in a single building in Texas is staggering. It is the ultimate manifestation of the founder's ego, backed by the largest pile of industrial capital ever assembled. We are watching the high-stakes architectural phase of a new digital era. The era of distributed, globalized hardware manufacturing is rapidly colliding with the hard physical limits of what is possible on Earth. The pivot to centralized, vertically integrated, and eventually space-based computing is not just a science fiction concept anymore. It is actively being poured into concrete and bolted into rocket fairings right now. The success or failure of the terafab will not just determine the valuation of Tesla or space exploration technologies. It will fundamentally dictate the physical location, the energy efficiency, and the ultimate ownership of the intelligence that will run the next century of human progress. We are moving from an economy constrained by the speed of cargo ships, carrying silicon wafers across the ocean, to an economy constrained only by the speed of light and the thermal radiation limits of the vacuum of space. And the transition is going to be incredibly volatile to watch